Okay, this is probably going to be a shorter one. I'm just going to try to finish off this book. It's this paging, and then fork exec, and then the epilogue, and I'll probably call it a day after that. So just jump right in. The translator in your in your computer. Up until now, every time I've talked about reading and writing memory, up until now, every time I've talked about reading and writing memory was a little wishy-washy. For example, ELF files specify specific memory addresses to load data into. So why aren't there problems with different processes trying to use conflicting memory? Why does each process seem to have a different memory environment? Also, how exactly did we get here? We understand that execv is a syscall that replaces the current process with a new program, but this doesn't explain how multiple processes can be started. It definitely doesn't explain how the very first programs run, what chicken processes, lays, spawns, all the other eggs, other processes. We're nearing the end of our journey. After these two questions are answered, we'll have a mostly complete understanding of how your computer got from boot up to running the software you're using right now. Memory is fake. So, about memory, it turns out that when the CPU reads from or writes to a memory address, it's not actually referring to that location in physical memory, RAM. Rather, it's pointing to a location in virtual memory space. I think I kind of knew that. The CPU talks to a chip called a Memory Management Unit, MMU. The MMU works like a translator with a dictionary that translates locations in virtual memory to locations in RAM. When the CPU is given an instruction to read from memory address 0xFFFAF548344067FE2, it asks the MMU to translate that address. The MMU looks it up in a dictionary, discovers that the matching physical address is this, and then sends the number back to the CPU. The CPU can then read that address in RAM. Hey, what's this? CPU asks. This guy, the MMU, looks in his dictionary and he says, it's that. I like this. This is a good drawing. When the computer first boots up, memory accesses go directly to physical RAM. Immediately after startup, the OS creates the translation dictionary and tells the CPU to start using the MMU. This dictionary is actually called a page table, and the system of translating every memory access is called paging. Oh, this is what paging is. That actually really makes sense. Okay, entries in the page table are called pages, and each one represents how a certain chunk of virtual memory maps to RAM. And these chunks are always a fixed size, and each processor architecture has a different page size. x86-64 has a default 4 kilobyte page size, meaning each page specifies the mapping for a block of memory 4,096 bytes long, which is 4 kilobytes. In other words, with 4 kilobyte pages, the bottom 12 bits of an address will always be the same before and after MMU translation. Wait, or is this that other thing that's not quite kilobyte? Because the 4 kilobytes would be 4,000, right? But there's this other thing. What does that stand for? Kilobyte, yeah. Okay. But it's basically equal to a kilobyte. So 4 gigabytes, kilobytes. x64 also allows operating systems to enable larger a megabyte or a gigabyte? 2 megabyte, I'll say megabyte and gigabyte pages, which can improve address translation speeds but increase memory fragmentation and waste. The larger the page size, the smaller the portion of that address's space translated by the MMU. This becomes a page start address, and this indexes the page. Okay. The page table itself just resides in RAM. While it can contain millions of entries, each entry size is only on the order of a couple of bytes, so the page table doesn't take up too much space. To enable paging at boot, the kernel first constructs the page table in RAM. Then it stores the physical address of the start of the page table in a register called the Page Table Base Register, PTBR. Finally, the kernel enables paging to translate all memory access with the MMU. On x64, the top 20 bits of the control register 3, CR3, function as the PTBR. Bit 31 of CR0, designated PG for paging, is set to 1 to enable paging. Okay. The magic of the paging system is what the page table can be is that the page table can be edited while the computer is running. This is how each process can have its own isolated memory space. When the OS switches context from one process to another, an important task is remapping the virtual memory space to a different area in physical memory. Let's say you have two processes. Process A can have its code and data likely loaded from an ELF file at that space, and process B can have its code and data from the very same address. Those two processes can even be instances of the same program because they aren't actually fighting over that address range. That's interesting. The data for process A is somewhere far from process B in physical memory and is mapped to this by the kernel when switching to the process. See, they both say read that, but then they go through the MMO and it maps it onto the RAM at some other location. That's really cool. Aside, cursed elf fact. Cursed elves. In certain situations, bin format elf has to map the first page of memory to zeros. Some programs written for Unix system V release 4.0 SVR4 on OS from 1988, that was the first to support elf, rely on null pointers before being readable. And somehow some programs still rely on that behavior. It seems like the Linux kernel dev implementing this was a little disgruntled. Why this, you ask? Well, SVR4 maps page 0 as read-only, and some applications depend upon this behavior. Since we do not have the power to recompile these, we emulate the SVR4 behavior. Sigh. Sigh indeed. Is this like a real GitHub comment or something? That's funny. That's really funny. Hey, you know what we can do? Can't you like blame these? Get to blame. How do you just want to blame? Oh yes, get blame. Or was it Sigh? Doesn't have the person. It's 20 years old though. Wow. Okay. Security with paging. The process isolation enabled by memory paging improves code ergonomics. Processes don't need to be aware of other processes' team's memory, but it also creates a level of security. Processes cannot access memory from other processes. This half answers one of the original questions from the start of the article. If programs run directly on the CPU and the CPU can directly access RAM, why can't code access memory from other processes or, God forbid, the kernel? Remember that? It feels like so long ago. It does feel like so long ago. What about the kernel memory, though? First things first, the kernel obviously needs to store plenty of data of its own to keep track of all the processes running and even the page table itself. Every time a hardware interrupt, software interrupt, or system call is triggered and the CPU enters kernel mode, the kernel code needs to access the memory somehow. Linux's solution is to always allocate the top half of the virtual memory space to the kernel, so Linux is called the higher half kernel. Windows employs a similar technique, while macOS is slightly more complicated, and it caused my brain to ooze out of my ears reading about it. Oh, this is horrible. This is it, I guess. It would be terrible for security if user-land processes could read or write kernel memory, though, so paging enables a second layer of security. Each page must specify permission flags. One flag determines whether the region is writable or only readable. Another flag tells the CPU that only kernel mode is allowed to access that region's memory. This latter flag is used to protect the entire higher half kernel space. The entire kernel memory space is actually available to the virtual memory mapping for user space programs. They just don't have the permission to access it. Here's a page table entry. Present, true. Read, write, read only. All modes, dirty, false, access true. That makes sense. The page table itself is actually contained within the kernel memory space. When the timer chip triggers a hardware interrupt for process switching, the CPU switches the privilege level to kernel mode and jumps to Linux kernel code. Being in kernel mode until ring 0 allows the CPU to access the kernel protected memory region. The kernel can then write to the page table, residing somewhere in that upper half of memory, to remap the lower half of virtual memory for the new process. When the kernel switches to the new process and the CPU enters user mode, it can no longer access any of the kernel memory. Just about every memory access goes through the MMU. Interrupt descriptor table handler pointers. Those address the kernel's virtual memory space as well. Okay. Hierarchical paging and other optimizations. 64-bit systems have memory addresses that are 64-bit bits long, meaning that the 64-bit virtual memory space is a whopping 16 exabytes. What's an exabyte? It's this many bytes. That's many bytes. This is incredibly large, far larger than any computer that exists today or will exist anytime soon. As far as I can tell, the most RAM in any computer ever was in the Blue Water supercomputer. Well, what's that? With over 1.5 petabytes of RAM. Holy smokes. That's still less than 0.01% of 16 exabytes. Blue Waters. Huh. That's interesting. This is it? Part of it? If an entry in the page table was required for every 4 kilobyte section of virtual memory space, you would need this many page table entries. What is that? 1,000, million, billion, trillion, quadrillion. With 8 byte long page table entries, you would need 32 petabytes of RAM. It's like a petabyte, but a petabyte of RAM just to store the page table alone. You may notice that's still larger than the world record for the most RAM in a computer. Aside, why the weird units? I know it's uncommon and really ugly, but I find it important to clearly differentiate between binary byte-size units, powers of 2, and metric ones, powers of 10. A kilobyte, KB, is an SI unit that means 1,000 bytes. A kibibyte, KIB, is an EIC recommended unit that means 1,024 bytes. In terms of CPUs and memory addresses, byte counts are usually powers of 2 because computers are binary systems. Using KB or worse KB to mean 1,023 would be more ambiguous. Since it would be, yeah, that's kind of what I figured out earlier, right? Since it would be impossible or at least incredibly impractical to have sequential page table entries for the entire possible virtual space memory space, CPU architectures implement hierarchical paging. In hierarchical paging systems, there are multiple levels of page tables of increasingly small granularity. The top level entries cover large blocks of memory and point to page tables of smaller blocks, creating a tree structure. Gotcha. The individual entries for blocks of 4 kilobytes or whatever the page size is are the leaves of the tree. x86-64 historically uses 4-level hierarchical paging. In this system, each page table entry is found by offsetting the start of the containing table by a portion of the address. This portion starts with the most significant bits, which work as a prefix, so the entry covers all addresses starting with those bits. The entry points to the start of the next level of the table containing the subtrees for that block of memory, which are again indexed with the next collection of bits. The designers of x64's 4-level paging also chose to ignore the top 16 bits of all virtual pointers to save page table space. 48 bits gets you a 128 something virtual address space, which is deemed to be large enough. That is pretty big, if that's like terabytes. The full 64 bits would give you 16 of that huge thing, which is kind of a lot. Since the first 16 bits are skipped, the most significant bits for indexing the first level of page table actually start at bit 47 rather than 63. This also means the higher half kernel diagram from earlier in this chapter was technically inaccurate. The kernel space start address would have been depicted as the midpoint of an address space smaller than 64 bits. And now we have a handy diagram. Level 4, one single top level table. Address of an L3 of a level 3 table has an address of a level 2, address of a level 1, and then it has actual RAM addresses. Okay, that makes sense. Hierarchical paging solves the space problem because at any level of the tree, the pointer to the next entry can be null. This allows entire subtrees of the page table to be elided, meaning unmapped areas of the virtual memory space don't take up any space in RAM. Lookups at unmapped memory addresses can fail quickly because the CPU can error as soon as it sees an empty entry higher up in the tree. Page table entries also have a presence flag that can be used to mark them as unusable even if the address appears valid. Another benefit of hierarchical paging is the ability to efficiently switch out large sections of the virtual memory space. A large swath of virtual memory might be mapped to one area in physical memory for one process and a different area for one other process. The kernel can store both mappings in memory and simply update the pointers at the top level of the tree when switching processes. If the entire memory space mapping was stored as a flat array of entries, the kernel would have to update a lot of entries, which would be slow and still require independently keeping track of the memory mappings for each process. I said x64 historically uses 4-level paging because recent processors implement 5-level paging. Oh. 5-level paging adds another level of indirection as well as 9 more addressing bits to explain the address space to 128 petabytes with 57-bit addresses. 5-level paging is supported by operating systems including Linux since 2017, as well as recent Windows 10 and 11 server versions. This is a nice website. Look at this. Don't make them like they used to, do they? Aside, physical address space limits. Just as operating systems don't use all 64 bits for virtual addresses, processors don't use entire 64-bit physical addresses. When 4-level paging was the standard, x64 CPUs didn't use more than 46 bits, meaning the physical address space was limited to only 64 terabytes. With 5-level paging, support has been extended to 52 bits, supporting a 4 petabyte physical address space. On the OS level, it's advantageous for the virtual address space to be larger than the physical address space. As Linus Torvalds said, it needs to be bigger by a factor of at least 2, and that's quite frankly pushing it, and you're much better off having a factor of 10 or more. Anybody who doesn't get that is a moron. End of discussion. Sounds like typical Torvalds. Typical Torvalds. Repeat after me. Swapping and demand paging. A memory access might fail for a couple of reasons. The address might be out of range, it might not be mapped to by the page table, or it might have an entry that's marked as not present. In any of these cases, the MMU will trigger a hardware interrupt called a page fault to let the kernel handle the problem. In some cases, the read was truly invalid or prohibited. In these cases, the kernel will probably terminate the program with a seg fault error. Definitely seen these before. Seg fault ontology. What's ontology? It's a branch of philosophy that deals with the study of the nature of being, existence, and reality. That's deep. Segmentation fault means different things in different contexts. The MMU triggers a hardware interrupt called a seg fault when memory is read without permission, but seg fault is also the name of a signal the OS can send to running programs to terminate them due to any illegal memory access. Okay. In other cases, memory access can intentionally fail, allowing the OS to populate the memory and then hand control back to the CPU to try again. For example, the OS can map a file on disk to virtual memory without actually loading it into RAM, and then load it into a physical memory when the address is requested and a page fault occurs. This is called demand paging. CPU says read this, and then there's a page fault, and the MMU gets confused, and then the page fault handler jumps in, says loading data into RAM, done, return from interrupt, and this guy says thanks. Oh, because this guy like swaps it out real quick, I guess. Okay. For one, this allows syscalls like mmap that lazily map entire files from disk to virtual memory to exist. If you're familiar with llama.cpp, a runtime for a leaked Facebook language model, I'm not, Justin Tunney recently significantly optimized it by making all the loading logic use mmap. If you haven't heard of her before, Justine, not Justin, sorry. If you haven't heard of her before, check her stuff out. Cosmopolitan, libc, and ape are really cool and might be interesting if you've been enjoying this article. Apparently there's a lot of drama about Justine's involvement in this change. Just pointing this out so I don't get screamed at by random internet users. I must confess that I haven't read most of the drama, and everything I said about Justine's stuff being cool is still very true. When you execute a program and its libraries, the kernel doesn't actually load anything into memory. It only creates an mmap of the file. When the CPU tries to execute the code, the page immediately faults and the kernel replaces the page with a real block of memory. Demand paging also enables the technique that you've probably seen under the name swapping or paging. Operating systems can free up physical memory by writing memory pages to disk and then removing them from physical memory, but keeping them in virtual memory with the present flag set to 0. If that virtual memory is read, the OS can then restore the memory from disk to RAM and set the present flag back to 1. The OS may have to swap a different section of RAM to make space for the memory being loaded from disk. Disk reads and writes are slow, so operating systems try to make swapping happen as little as possible with efficient page replacement algorithms. Page replacement algorithm. I don't understand how there's a Wikipedia article for literally everything. An interesting hack is to use page table physical memory pointers to store the location of files within physical storage. Since the MMU will page fault as soon as it sees a negative present flag, it doesn't matter that they are invalid memory addresses. This isn't practical in all cases, but it's amusing to think about. Okay. Let's talk about forks and cows. This is exciting. The final question. How did we get here? Where do the first processes come from? This article is almost done. We're on the final stretch, about to hit a home run, moving on to greener pastures. Oh wow, this is so nice. And various other terrible idioms that mean you are a single length of chapter 6 away from touching grass or whatever you do with your time when you aren't reading 15,000 word articles about CPU architecture. Okay, if exec_v starts a new program replacing the current processes, how do you start a new program separately and a new process? This is a pretty important ability if you want to do multiple things on your computer. When you double click an app to start it, the app opens separately while the program you were previously on continues running. The answer is another syscall, fork, the system call fundamental to all multiprocessing. Fork is quite simple actually. It clones the current process and its memory, leaving the saved instruction pointer exactly where it is, and then allows both processes to proceed as usual. Without intervention, the programs continue to run independently from each other and all computation is doubled. The newly running process is referred to as the child, while the process originally calling fork the parent. With the process originally calling fork the parent. Processes that call fork multiple times, processes can call fork multiple times, thus having multiple children. Each child is numbered with a process ID, PID, starting with 1. Cluelessly doubling the same code is pretty useless, so fork returns a different value on the parent versus the child. On the parent, it returns the PID of the new child process, while on the child it returns 0. This makes it possible to do different work on the new process, so that forking is actually helpful. Okay. You say like, let this guy be the fork. Result of forking. Code continues for this point as usual, but now across two identical processes. Identical except for that the PID returned from the fork. Except for the PID returned from the fork. Okay. This is the only indicator to either program that they are not one of a kind. If PID equals 0, we're in the child. Do some computation and feed results to the parent. Otherwise, we're in the parent. Probably continue whatever we were doing. Process forking can be hard to wrap your head around. From this point on, I will assume you've figured it out. If you have not, check out this hideous looking website for a pretty good explainer. This is beautiful. I'm not sure that I really have my head wrapped around it. I think I get it. It clones the current process and its memory, leaving the saved instruction pointer exactly where it is, and then allows both processes to proceed as usual. I mean, that kind of makes sense. Anyways, Unix programs launch new programs by calling fork and then immediately running exec_v in the child process. This is called the fork exec pattern. When you run a program, your computer executes code similar to the following. This is like the same as above. If it's 0, then we exec_v with it. Otherwise, or not otherwise, but down here, we got here the process didn't get replaced. We're in the parent. Hopefully, we also now have the PID of the new child access process in the PID variable if we ever need to kill it. Parent program continues here. Moo. You might have noticed that duplicating a process's memory only to immediately discard all of it when loading a different program sounds a bit inefficient. Luckily, we have an MMU. Duplicating data in physical memory is the slow part, not duplicating page tables. So we simply don't duplicate any RAM. We create a copy of the old process's page table for the new process to keep the mapping pointing to the same underlying physical memory. Okay. But the child process is supposed to be independent and isolated from the parent. It's not okay for the child to write the parent's memory or vice versa. Introducing cow, copy on write pages. With cow pages, both processes read from the same physical address as long as they don't attempt to write to the memory. As soon as one of them tries to write to the memory, that page is copied and RAM. Cow pages allow both processes to have memory isolation without an upfront cost of cloning the entire memory space. This is why then there's a later cost if you do decide to write, I suppose. This is why the fork exec pattern is efficient. Since none of the old processes memory is written is written to before loading a new binary, no memory copying is necessary. Cow is implemented, like many fun things, with paging hacks and hardware interrupt handling. After fork clones the parent, it flags all the pages of both processes as read-only. When a program writes to memory, the write fails because the memory is read-only. This triggers a segfault, the hardware interrupt kind, which is handled by the kernel. The kernel, which duplicates the memory, updates the page to allow writing, and returns from the interrupt to reattempt the write. Knock knock, who's there? Interrupt cow, interrupt cow. So it's just like that. In the beginning, not of the Bible. Every process on your computer was fork exec by a parent program except for one, the init process. The init process is set up manually, directly by the kernel. It is the first userland program to run and the last to be killed at shutdown. Want to see a cool instant black screen? If you're on macOS or Linux, save your work, open a terminal, and kill the init process. I do want to try that. Is that gonna stop my recording though? That sounds fun. Okay, we'll hold off for a second. Author's note: knowledge about init processes unfortunately only applies to Unix-like systems like macOS and Linux. Most of what you learn from now on will not apply to understanding Windows, which has a very different kernel architecture. Just like the section on execv, I am explicitly addressing this. I could write another entire article on the NT kernel, but I'm holding myself back from doing so for now. The init process is responsible for spawning all the programs and services that make up your operating system. Many of those, in turn, spawn their own services and programs. Init spawns all these guys, and they can spawn their own guys. Okay. Killing the init process kills all of its children and all their children, shutting down your OS environment. Back to the kernel. We had a lot of fun looking at Linux kernel code back in chapter 3, so we're going to do some more of that. This time, we'll start with a look at how the kernel starts the init process. Your computer boots up in a sequence like the following. The motherboard is bundled with a tiny piece of software that searches your connected disks for a program called the bootloader. It picks a bootloader, loads its machine code into RAM, and executes it. Keep in mind that we are not yet in the world of running OS. Until the OS kernel starts it on init process, multiprocessing and syscalls don't really exist. In the pre-init context, executing a program means directly jumping to its machine code and RAM without expectation of return. The bootloader is responsible for finding a kernel, loading into RAM, and executing it. Some bootloaders, like Grub, are configurable and or let you select between multiple operating systems. BootX and Windows Boot Manager are the built-in bootloaders of macOS and Windows, respectively. Okay. So this is what I'm going to write my own of, is a bootloader, I guess. The kernel is now running and begins a large routine of initialization tasks, including setting up interrupt handlers, loading drivers, and creating the initial memory mapping. Finally, the kernel switches the privilege level to user mode and starts the init program. Okay, we're finally in userland in an operating system. The init program begins running init scripts, starting services, and executing programs like the shell UI. Cool. Initializing Linux. On Linux, the bulk of step 3, kernel initialization, occurs in the start kernel function in that file. This function is over 200 lines of calls to various other init functions, so I won't include the whole thing in this article, but I do recommend scanning through it. At the end of start, let's go check it out. At the end of start kernel, a function named arch call rest init is called. Where is it? Here, okay. Start kernel. It's basically just calling out to like a million other functions that do interesting things. And this is the thing that was referenced in the article at the end there. What does non-initted mean? The start kernel function is defined as ASM linkage visible void init no sanitized address start kernel void. The weird keywords like underscore underscore visible underscore underscore init and underscore underscore no underscore sanitized underscore address are all C preprocessor macros used in the Linux kernel to add various code or behaviors to a function. In this case, init is a macro that instructs the kernel to free the function and its data from memory as soon as the boot process is completed, simply to save space. How does it work? Without getting too deep into the weeds, the Linux kernel is itself packaged as an ELF file. The underscore init macro expands to section init.txt, which is a compiler directive to place the code in a section called .init.txt instead of the usual .text section. Other macros allow data and constants to be placed in special init sections as well, such as init data that expands to .init.data. Arch call rest init is nothing but a wrapper function around rest init. The comment said do the rest non-initted because rest init is not defined within the init macro. This means it is not freed when cleaning up init memory. Okay. Rest init now creates a thread for the init process, like this. The kernel init parameter passed to user mode thread is a function that finishes some initialization tasks and then searches for a valid init program to execute it. This procedure starts with some basic setup tasks. I will skip through these for the most part, except for where free init mem is called. This is where the kernel frees our .init sections. Okay. Now the kernel can find a suitable init program to run. We try each of these until one succeeds. The bourne shell can be used instead of init if we are trying to recover a really broken machine. Okay. Okay. On Linux, the init program is almost always located at or symbolic link to this place. Common inits include systemd, which has an abnormally good website. I like abnormally good websites. Whoa. I mean, abnormally good as in it's like clean compared to the other documentation websites I've been linked to. And open source. Systemd. Huh. OpenRC and CDD is not as good. That was not too bad. That one's sort of poor. Will default to bin sh if it can't find anything else. If it can't find bin sh, something is terribly wrong. That's, I guess, down here, right? macOS has an init program too. It's called launchd and is located at sbin launchd. See, now I've run into this before. That's interesting. Try running that in a terminal to get yelled at for not being a kernel. Let's try it. How? Wait, can I just make you smaller so that you're not in the way? Ready? Experimentation. sbin launch d cannot be run directly. Well, from this point on, we're at step 4 in the boot process. The init process is running in userland and begins launching various programs using the fork exec pattern. Fork memory mapping. I was curious how the Linux kernel remaps the bottom half of memory when forking processes, so I poked around a bit. Kernel forkc seems to contain most of the code for forking processes. The start of that file helpfully pointed me to the right place to look. Forkc contains the help routines for the fork system call. See also entry.s and others. Fork is rather simple once you get the hang of it, but the memory management can be annoying. See memory.c. It looks like this copy page range function takes some information about memory mapping and copies the page tables. Quickly skimming through them, the functions it calls, this is also where pages are set to be read-only to make them cow pages. It checks whether it should do this by calling a function called isCowMapping. is cal mapping is defined back and include Linux mm.h. It returns true if the memory mapping has flags that indicate the memory is writable and isn't shared between processes. Sharing memory doesn't need to be cowed because it is designed to be shared. Admire the slightly incomprehensible bit masking. Okay. Back in kernel fork.c, doing a simple command F for copy page range yields one call from the dup mmap function, which is dupe probably, which is in turn called by dupe mm, which is called by copy mm, which is finally called by the massive copy process function. Copy process is the core of the fork functions and in a way the center point of how Unix systems execute programs, always copying and editing a template created for the first process at startup. Now we need to watch this video. That was really disturbing. In summary, so how do programs run? On the lowest level, the processes are dumb. They have a pointer into memory and execute instructions in a row unless they reach an instruction that tells them to jump somewhere else. Besides jump instructions, hardware and software interrupts can also break the sequence of execution by jumping to a preset location that can then choose where to jump to. Processor cores can't run multiple programs at once, but this can be simulated by using a timer to repeatedly trigger interrupts and allowing kernel code to switch between different code pointers. Programs are tricked into believing they're running as a coherent, isolated unit. Direct access to system resources is prevented in user mode. Memory space is isolated using paging, and system calls are designed to allow generic I/O access without too much knowledge about the true execution content. System calls are instructions that ask the CPU to run some kernel code, the location of which is configured by the kernel at startup. But how do programs run? After the computer starts up, the kernel launches the init process. This is the first program running at the higher level of abstraction, where its machine code doesn't have to worry about many specific system details. The init program launches the programs that render your computer's graphical environment and are responsible for launching other software. To launch a program, it clones itself with a fork syscall. The cloning is efficient because all the memory pages are cow and the copy on write, and the memory doesn't need to be copied within physical RAM. On Linux, this is the copy process function in action. Both processes check if they're the forked process. If they are, they use an exec syscall to ask the kernel to replace the current process with a new program. The new program is probably an ELF file, which the kernel parses to find information on how to load the program and where to place its code and data within the new virtual memory mapping. The kernel might also prepare an ELF interpreter if the program is dynamically linked. The kernel can then load the program's virtual memory mapping and return to user land with the program running, which really means setting the CPU's instruction pointer to the start of the new program's code in virtual memory. Epilogue. Congratulations. You have now firmly placed the U in CPU. I hope you had fun. I did have fun. That was good. I'll send you off by emphasizing once more that all the knowledge you just gained is real and active. The next time you think about how your computer is running multiple apps, I hope you envision timer chips and hardware interrupts. When you write a program in some fancy programming language and get a linker error, I hope you think about what that linker is trying to do. If you have any questions or corrections about anything contained in this article, you should email me there or submit an issue PR on GitHub. The end. But wait, there's more. There's bonus tidbits. We'll read it. Bonus, translating C concepts. If you've done some low-level programming yourself, you probably know what the stack and the heap are, and you've probably used malloc. Yes, in the past. You might not have thought a lot about how they're implemented. First of all, a thread stack is a fixed amount of memory that's mapped to somewhere high up in virtual memory. On most, though not all architectures, the stack pointer starts at the top of the stack memory and moves downward as it increments. Physical memory is not allocated upfront for the entire map stack space. Instead, demand paging is used for lazily allocated memory as frames of the stack are reached. It might be surprising to hear that the heap allocation functions like malloc are not system calls. Instead, heap memory management is provided by the libc implementation. Malloc, free, et al. Are all complex procedures, and the libc keeps track of memory mapping details itself. Under the hood, the userland heap allocator uses syscalls including map, which can map more than just files, and this thing. Bonus tidbits. I couldn't find anywhere coherent to put these, but found them amusing, so here you go. Here's a quote. Most Linux users probably have a sufficiently interesting life that they spend little time imagining how page tables are represented in the kernel. That's nice. An alternative visualization of hardware interrupts. Move rags RBX. This is assembly, right? Add rags. Hello, it's me, the keyboard. I have an important message. E. That's nice. That's funny, actually. I know that some system calls use a technique called VDSOs instead of jumping into kernel space. I don't have time to talk about this, but it's quite interesting and I recommend reading into it. Okay. And finally, addressing the Unix allegations, I do feel bad that a lot of the execution-specific stuff is very Unix-specific. If you're a Mac OS or Linux user, this is fine, but it won't bring you too much closer to how Windows executes programs or handles system calls, although the CPU architecture stuff is all the same. In the future, I would love to write an article that covers the Windows world. Acknowledgements. I talked to GPT 3.5 and GPT 4 a decent amount while writing this article. While they lied to me a lot and most of the information was useless, they were sometimes very helpful for working through problems. LLM assistants can be net positive if you're aware of their limitations and are extremely skeptical of everything they say. That's a good take. I like this. That said, they're terrible at writing. Don't let them write for you. Yes, that is true. More importantly, thank you to all the humans who proofread for me. Okay. I am a teenager. Oh, this is the thing I found earlier. But see, on Monday, it's Thursday. On Monday, I'm going to be 20, so I probably wouldn't get into time. All the mediocre art on this article was drawn in Figma. I used Obsidian for editing and sometimes Veil for... What's Veil? The markdown source for this article is available. Yeah, okay. What is Veil? Huh. All right, cool. We finished it. So, yeah, I guess I'll stop there. I'm hoping next or tomorrow, whenever I do the next video, to start learning some more assembly or maybe some C, or we'll see. We'll see what happens.